The equivalence point of a titration is when you have mixed an acid and base in stoichiometric amounts so that they completely neutralize each other. This can be estimated by using an indicator, which is a chemical that changes color based on pH. The end point of a titration is defined as when the indicator changes color and you stop mixing the acid and base together. You always, in a titration, want the equivalence point and the end point to be as close to each other as possible so that you avoid error. Different indicators change color at various pHs. Since the salt produced in a neutralization reaction may affect the pH of the final solution, the pH at equivalence may not always be 7. You must always choose an indicator for your titration that changes color as close as possible to the pH at the equivalence point in order to have an accurate titration. Below are some common indicators and the pH ranges that they change. Here's an example of how to calculate the pH at equivalence and also to pick an appropriate indicator to use in a titration lab. We're going to react magnesium hydroxide and acetic acid together. The first thing that you need to do is figure out what kind of salt is produced during the titration. If it is a neutral salt, then you'll end up with pH 7 at equivalence, and you would just have to pick an indicator that changes color around 7. If it's an acidic or a basic salt, you would calculate the theoretical pH at equivalence and then determine the indicator. This would be a double displacement reaction where my magnesium will go with the acetate and the hydrogen falling off of the carboxylic acid will join with the hydroxide and make water. Because magnesium is in group 2, magnesium hydroxide is a strong base. Because ethanoic acid is a carboxylic acid, then it's a weak acid, and I will not have pH 7 at equivalence because I'm not going to make a neutral salt. The Mg2 plus in my salt will be a weak conjugate acid, but the acetate ions that are present will be strong conjugate bases. That means I will have a pH that is greater than 7. Well, how far away from 7 will it be? I need to use some stoichiometry to find the concentration of that acetate in my system at equivalence. If I take the concentration of my magnesium hydroxide and times it by my volume in liters, that will give me how many moles I have. I then have a 1-to-1 mole ratio. Now, it does not matter whether you use your magnesium hydroxide or your information about your acetic acid in the stoichiometry problem. That's because we're calculating the pH at equivalence, which means that there's no limiting reactant. They are equally added in. However, I do need to know the volume of acetic acid that I used in order to divide it by my moles to find my molar concentration initial in my equilibrium. I have a 1-to-2 mole ratio from my magnesium hydroxide to my ethanoic acid, Because they are the same concentration, and I have a 1 to 2 mole ratio, then I will need double the amount, so 40 mils. So to find the concentration of my magnesium acetate, I will divide that by the total volume of 60 mils, expressed in liters. But this is the concentration of magnesium acetate. Only the acetate affects the pH. There is a 2 to 1 mole ratio between acetate and magnesium acetate, because for every MgCH3COO bracket 2 that falls apart, I'll get 1 acetate. That gives me an initial concentration of 0.133 moles per liter. I'll now write a Bronson-Lowry equilibrium using my strong conjugate in my salt. Because acetate is a base, it will accept a proton from the water and make hydroxide ions. From my stoichiometry above, I know the initial concentration is 0.133. And because I'm at equivalence, there will be no acetic acid initially in my system. If I find the concentration of hydroxide at equilibrium, I can change that into pH. However, this is a base equilibrium, so I need to solve for x using a Kb. I haven't been given one, but I can look up the Ka of acetic acid in the back of my book and convert it into a Kb by using the Ka times Kb equation. Kb will equal the concentration of my products raised to their coefficients divided by the concentration of my reactants raised to their coefficients, ignoring water. I want to avoid doing quadratic formula, so I check the assumption and it works. That means if I subtract x from 0.133, I'll get 0.133. 0.133 times 5.6 times 10 to the minus 10 will equal x squared. If I take the square root of that, that gives me x. If I take the negative log of x, that will give me the pH of the solution, or the pOH of the solution. Therefore, the pH at equivalence will be 14 minus the pOH, which equals 8.9. For question B, if I wanted to do this titration and mix magnesium hydroxide and ethanoic acid together, and use an indicator to tell me when I've reached stoichiometric amounts, I would need to find an indicator that changed colors at pH 8.9. If we have a look at the chart, we have a couple of options. I could use thymal blue. It would be yellow as I approached equivalence, change green when I'm just at 8.9, and then turn blue if I went too far. Or another indicator I could use would be phenolphthalein. It would be clear and turn slightly pink when I reach the equivalence point. If I use these two indicators, I would be strategically making my endpoint when I start my titration, when my indicator changed color, as close to the equivalence point as possible to avoid error.